Hello and welcome back to ST118 Statistics and Applications, Session 4. In this session, we like to discuss more about three population means tests. All right, so three or more population means test. Okay, so meaning it will involve mu1, mu2, mu3, and more. All right, so there's no technical limitation. You can have as many populations as you want if your budget allows to take so many measurements and data capturing, okay, with sufficient precision. And as usual, we like to just spend a bit of time to talk about the application areas because this is more like the reverse of homework, right? So for you to be really cashing out on the statistics skills and knowledge that you have learned from these video sessions, you put in the time to learn them, right? And I put in the time to teach you, convey that information, that skill to you. So once you have put in the time, you want to encash it, make the full use of it, derive the highest value for your personal career development, life, and all that. That is where I like to discuss more for this particular topic, right? The reverse of homework. You are the one to identify the homework for yourself. Okay. Then we talk about the specific calculations involved in this kind of test and illustrate it with an example. Okay, so let's just go right in, right? So this test, this family of category of problems, it's got three or more population means test. And another word for this is the famous ANOVA test. ANOVA test. Who knows what this word ANOVA means? Okay, I'm hearing some of you saying analysis of variance, right? Analysis, AN, don't know why. Of, seldom of deserves one letter in the acronym itself. Of variance, again var, right? VA, variance. Analysis of variance, but the goal is to test for the equality of the means here, right? So right off, let's just look at how the hypothesis looks like. So the reason why I start with the hypothesis is because it is fixed. So fixed that in the past I've been observing many batches of students, they always do well because no longer do you have to worry about what's the claim. Claim goes to H1, except equality claim. Is this equality? Oh, this is equality claim, right? You'll see why. But so the hypothesis is fixed, never changing for any kind of ANOVA problem, any kind of three or more population means test. 5 population means test, same hypothesis, right? With a bit of just extension, that's all. Let's just look at how it looks like. So you just, in null hypothesis, we state and assume to be true, right, until proven otherwise by data, that mu1 equals to mu2 equals to mu3. And if you have 3 populations, you stop there. I'm just going to give you a bit of a ... to illustrate that you can extend to k populations. K can be 5, can be 10. Seldom does it get to 30, 50, but who knows, right? Maybe in e-commerce, capture everything. The time delay, the time of connection, the number of clicks before you purchase. So there are many more numbers and data that potentially one can capture automatically, cheaply, efficiently. And then you have, for a particular user, 100 different measurements. So it can be that you have 100K. So who knows? So the good thing, the power of this thing is that it is very, very flexible, right? You can extend this to 100 populations if your system captures those data more or less reliably, right? So here the H1 is at least one of mu I, right, is different. We use the word different to signal that it is not equal, right? Not equal. Not equal can be larger, can be smaller. So you can't say whether it's less than or greater than. Where I is from 1 to k. At least one, at least one. So the reason is some students will say, wait, before I continue, there's another alternative version that we can say, sometimes we can say the not of H naught. So the best version is actually not all mu i's are equal, right? Because H naught says all the mu i's are equal, right? So the I ranging from 1 to k as usual. Right? Not of the statement is always logically correct as a mutually exclusive statement, right? So not all mu i's are equal is very, very acceptable. At least one of the mu I is different is also commonly seen in textbooks and is also correct logically, because what it's saying is that at least one. So I don't know which one, but at least one. For example, mu3 is so different from H naught that you cannot say mu3 is just varying in a statistical sense, so ignore it. Right? For example, all are 2, 2, 2.5, 3, sorry, 2, then 2, 2, 2. So the 2.5 is so outstanding, right, that it is different. So at least one of the mu I don't know which I, but one of it is different. Can be two or more, right? Or can be all are different. So the wrong thing to say is H1, all mu i's are different. Because you're asserting that after my test of ANOVA, mu1 is different from mu2, which is different from mu3, which is different. It's like this is 1.1, this must be 1.2, cannot be 1.1. This has to be 1.3, 2.5, cannot be 1.1. You know, who says that, right? There's no constraint forcing the mu i's to be different or detecting that they are all unique, right? That's a very strong statement, very rich in information. So where have you derived that conclusion right now? So the wrong thing to say is that all are different. That's another mistake that some students, fortunately not a lot, during exam, they would just say all are different. Okay, so that means you need to revise your logic a little bit. Huh? Some students will write not of this, that's correct. Some students will remember what they learned from textbook, at least one of this is different. So I stick to this one because it's also a little bit more illuminating. That means it's telling us, hey, not all are equal also means one or more could be different, right, from the rest. Okay, so this hypothesis is fixed. That's another information that is useful. All right, so let's just write that down. Okay, fixed for all ANOVA tests. So you don't really have to, in a way, analyze the problem as to whether it's less than, greater than, where to put H naught, put H naught. No need. So just stick to this statement. So fixed is good, but it's also very rigid in the sense that it only allows us to state this. It only allows us to check, are all equal or not? Right? The conclusion is either you do not reject, then all are equal, or you reject, then not. Right? So the output information is very little. Very little. So imagine you collected 100 sets of population samples, and all that it comes out is they are the same statistically, right? Or no. So the output is very, very little. It's almost like a 1-bit information output. So that's the sort of cons, perhaps, right? However, right, because it is still very much used in practice, there has to be a reason why it is very useful. And that's the application areas I like to go into after exposing the structure of the or the rigidity of the hypothesis statement for ANOVA in front of you. All right, so let's just go into the application areas. What might be the application areas? Okay, number one is they they are of course trying to compare, to judge, to assess, to make decisions, of course, right? So I emphasize that a lot in the one population mean test because there's a standard reference, there's a number, there's a hypothesized mean, right? So that is our standard. Did you meet the standard? So that will be a one population mean test. Did this item, did this measurement, did this product, this person, right, meet the standard? So that's the one population mean test. The two population mean test is relative judgment, right? So we are not interested in knowing whether the measurement meets certain predetermined number, right? So we just need to know, given two groups, two measurements, two persons, two products, two models, two entities, is one better than the other? So there's some sort of a win-loss case, right? So it's like zero-sum game, a win-loss case. Judgment, plaintiff and accused, right? So like in a legal proceeding, who wins, who loses. So that's the kind of judgment that we talked about in two population tests. What about three population tests? Clearly, we are also doing some sort of a judgment. Except, I think let's make it a little bit more specific, right? What sort of judgment are we talking about? First, I can think of, right, is fairness. So whenever you want to talk about fairness, we want to always talk about fairness, but you know what I'm trying to say, right? You are in a situation where you are maybe you are the executive, the manager, needing to ensure fairness. Okay, maybe not someone having a complaint in front of you, but you are ensuring, right? So as a sort of a quality check of the policies, you want to check whether there is fairness in the execution of this policy, right? Even though nobody complains, but because of your good nature, you want to ensure that fairness is still prevailing in this company, in this policy, whether it's HR policy, compensation policy, traveling policy, expense claim policy, promotion policy, whatnot, right? That fairness is still enforced, even and especially even if nobody complains, we ensure policy. We ensure fairness. So you want to check in a statistical sense rather than you just look at some numbers. I think it's fair. You know, that's very subjective fairness, right? So when you want to ensure fairness, say across groups, across categories, right? Across time, time wise, not so. It's like one person, right? Receiving income, then across time gets more and more. Is that fairness? We don't use the word fairness this way, right? Are you fair to yourself, right? It doesn't make much sense. So yes, we can capture a person's income over time, and then that will be the multiple sampling of the person's income, right? So the income is a variable. Over time, we get that multiple samplings, but that wouldn't quite involve ANOVA. That wouldn't quite involve our sense of fairness. Am I fair to myself? You know, that kind of discussion. So I probably won't put in time here, right? But across groups and categories, groups are usually people. Categories would be more like non-animate objects like product groups, right? Or batches. So manufacturing batches. Fairness is more like a notion for people. So even for categories, I wouldn't quite associate with non-animate objects, more like people. All right. So groups and categories, when you have to ensure fairness across them, Okay. For example, working hours. Okay, working hours. Is it the same across the groups? Okay, is it the same across accounting departments? Right, departments. Yeah, I think that's something we encounter a lot. Departments. Is it statistically similar, right, across departments? Uh, in order to ensure some sort of a fairness, right? So during COVID-19, even managers have to managers, even directors, have to take duty roster to uh, ensure that people check in with their pass or something, right? To ensure that it is traceable. So, is it fair across the various ranks? Right. So you can do some sort of a statistical check, and that would be the place where you use ANOVA. The other one is I can think of is the tiered differences. In a way, it's a kind of reversed fairness. You want to check that it is unfair. Why? Okay, I'll give you an example why, right? So example, uh, gold card membership, right? Gold, silver, and classic. So a particular financial firm or whatnot gives out memberships, right? Or maybe gym, right? Gym franchise chain gives out membership, gold, silver, classic, and you guys see this a lot, right? So I'm a gold member, I'm a silver member. So are they given unfair treatment because gold members pay more annual fees, silver a bit less, classic doesn't pay, for example? Then and yet after testing, you do not reject H naught. That means the benefit value maybe is annual benefit value for gold is the same statistically speaking as silver as classic. Then you say, wow, that's strange, right? So you're ensuring, you want to make sure that it's tiered differences. So it is more like you are expecting to reject H naught when you are actively pushing out tiered differences, right? Hey, join gold member, just paying 999 per year and you get to enjoy value that's worth 3,999, something like that. Okay, so if after maybe if you do the raw sampling raw estimation of the value worth, you might get the sense that, oh, annually gold is, I'm getting back uh, let's say just 1955, right? Silver, I'm getting back 1845. Classic, I'm getting back a value worth of about 1825 or 1800. Okay, so there is a sort of a manifest, right? Just based on the average, it looks like gold has more benefits than silver than classic. But if you perform ANOVA can detect that little bit of $100 difference, $50 differences in the annual benefits that a member in Gold Silver Classic gets back. It's just due to random noise. It's not significant difference enough for us to reject H naught. So that despite looking at the average sampled benefits from Gold, Silver, Classic, looking at them, they look different and they are tiered, right? Gold having more than silver, silver having more than classic. After performing ANOVA, you might find that, hey, you fail to reject H naught. So actually, it's not fair, right? That gold members are paying so much annual fee to subsidize classic members, something like that. So in these differences, so tier differences can also be applied to many other cases, not just membership, but of course, we are more familiar with this notion. Have same benefits and you want them to be different because you have designed them to be different, right? Okay. So it's like the reverse of fairness. That's what I'm saying. Then we have we have what is called uh, multiple party equality, right? So because of clearly the hypothesis allows for multiple party equality comparisons. Now, why is this different from fairness comparisons? Cannot talk and write at the same time. Okay. Why is this different from fairness? Because fairness, you want to make sure that it is so. You're sort of like assessment and then judgment, right? Comparisons, maybe it's just for info. Maybe it's not an immediate action thing. Not a that means ensuring equality, ensuring equal performance, for example, is not a policy, it's not a goal, right? You just curious, you just want to have a benchmark reference. So maybe in the boardroom, someone might say, all the branches and all the stores, they are basically the same, So why must you give more marketing budget to the Orchard Road stores, because the store manager is this guy's arch enemy in the company, right? So that could give rise to such a sweeping conclusion without proof, and then we test, right? Example: all 5 stores perform equally. All right. All 10 classes. Now, classes are not restricted to just university. That's not because I am having classes, that's why I just use classes. Uh, Perform equally. But classes can also be in commercial training classes, and even in MNCs, they have their own university. So there will be this class structure that can be easily copied from university settings, right? Because it's running so well already, there's no need to reinvent the wheels. There can be HR onboarding classes. You may call it batches, you may call it sessions, right? But people are associated to the batches, associated to the sessions. The notion is the same as classes. So are all the 10 classes performing equally? If not, something is strange, right? Or in certain cases, if not, like all 5 stores performing equally, if not, then that's the norm, right? Because some stores are in the touristy zone, that's why they sell better, right? Other stores are just to cover ground, make sure competitors are not there, but they don't do very well. We know that already. So it's not about ensuring fairness, right? But about just kind of a routine check. Fairness, however, is a driven motivation. We have to ensure that it's fair, something like that, right? So that's why I make the difference there. All 7 manufacturing or financial or utility stocks, right? Perform equally or not, right? Are EV, petrol, and hybrid models equally efficient? Perform equally. Perform will be based on the performance you're interested in. Could be fuel efficiency, mileage, length of use before first maintenance, whatever it is, right? So you can get the idea, right? And one category or one application area that I thought was very interesting would be solution or proposal comparison. So you see that in life we face a situation, right? A sort of a problem, and this kind of problem may require some sort of solution, as in a combination of people, materials, and services to get it done. For example, it could be that we have a problem, a business opportunity, a problem where we have to, prepare the stage for this Lady Gaga's performance in Singapore, right? Okay, so the demands are very, very complex, and so the whole solution to ensure that the 3-day performances, they are all smooth and exciting and entertaining, and of course we bring a lot of money. What are the ideas available? So you kind of tender it out, and solution providers will submit proposals, and they are not simple, right? There are pages and pages of drawings, diagrams, plans, explanations, and all that. So I'm talking about those. Now those you will of course evaluate them and finally select, isn't it? And typically there's an evaluation panel or even multiple evaluation panels examining from the perhaps the solutioning perspective, efficiency perspective. Let's say if there's a sustainability part, then power use, power use. This is very good, but uses a lot of power, right? And then value proposal, whatnot. So various aspects. Ultimately, those evaluations will have to be combined into a number, right, to rank. And so that number will be probably the sort of attractiveness index of this and this and this proposals. Okay, so I'm talking about those. So when you have these, typically involving some like ideas, right? Ideas, designs, strategies, even. So 3 consulting companies trying to provide marketing strategies, right? So proposals, and we convert them to numbers. Are all these ideas the same? So that's one big question. Are all these ideas equally equally good or bad? That means ANOVA can answer the question of they're all equal, right? So we will have to use our human judgment to decide if, hey, these few all look very exciting. ANOVA says they're all equal, means the other few that I personally am not interested in likely is also, right, in the judgment of the entire panel, equally good. Okay, so maybe I prefer more exciting lights. Another panel prefer more exciting dances, right? Which I don't appreciate, for example. So that's why. So if ANOVA does not reject the null hypothesis, then we conclude that they're all equally good. Then okay, so that suggests something because that's new information, right? That's a more objective information, and so then we can decide what to do. We can interview them, right? Ask them to present their proposals. Maybe there are some little details that didn't really come alive when we are reading the proposals. That means, in other words, we find ways to distinguish them, knowing that all the axis of assessments that we have gone through failed to distinguish one much more significantly than the other, right? So that's, but if rejected, then that's another information ANOVA is giving us. There's a hidden gem, right, somewhere. Because for complex solutions and proposals, it is less likely, I won't say totally impossible, but less likely, let's just say unlikely that they are automatically ranked. Like one is super good, the other one is second, the other one is third. Rank based on what criteria, right? We have experts in our panel. So it's unlikely that when ANOVA rejected them, it's automatically ranked. There's one particular gem, right? Something like that. Then all are gems, but they degrade in quality. So it's likely that if all are submitted by reputable vendor suppliers, maybe one is so outstanding, right? That is outlier in the market, right? So that's why ANOVA says no, 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 no. One of it is very, very good. You just need to find out which one. So if you have a short list of 3, then it's not difficult. If you have short list of 7, then it may need a little bit more combing. But that's worth it because these are finalists, right? So the gem deserves time to be put in to be identified. So I think these are very real life situations that we commonly encountered, and now I hope you will associate these situations to link with ANOVA, right? Then you can be the one taking the initiative to say, hey, you know what? Let's not speculate and give personal subjective assessment. That can come later. But for now, let's gather data and do an ANOVA analysis, something like that. Okay. All right. So that's for our application areas. Um, so 2 points I'd like to make before we move on. That is that the K here, I am trying to say 3 or more population mean stats, right? Where is it? Upstairs. Yeah, 3 or more population mean stats. So the K is 3 or more. But actually, K can be as few as 2 even. So 2 or more, that's already good enough. Furthermore, ANOVA test when K is 2, remember we talked about 2 population mean stats, right? When K is 2, we need to consider or assume that the population uh, distribution, the parent distributions, they are normal and the two populations have equal variance, or else we use the Welsh Satterthwaite formula. In ANOVA's case, when K is 2, that is mimicking the equality test, right, for two population. Then these assumptions are actually quietly made. So it is assuming that all parent distributions, and that extends to when K is 10 or 20, are 1, normal, and 2, have equal variance. As an equality test assumption. So even when K is 2, then how does it fit into the two population means test, correct? Yeah. And that would branch into the unpaired. Right. So unpaired. Well, it's already unpaired because you can't pair them, right? It's unpaired test, unpaired t-test with equal variance assumption. Variance, not variance. Variance assumption. And because it's t-test, the parent distributions are assumed to be normal. Yep, okay. And it is t-test, right? It is t-test. But in ANOVA, we use the F test statistic. And that's the next point I want to get into. The test statistic that we use is actually the F test statistic. So test statistic is the F test statistic. And it is what we call the SST over K minus 1. Now we know what is K, right? K is the number of groups we call, or population means, divided by SSE over N minus K. So K is the number of population means. SST is what we say as the sum of squares. So let's talk about what is SST. SST. So SST is the sum of squares of differences or deviations from the entire mean. Sum of squares of deviations from overall mean. I'll just denote as X bar. Of the group means weighted by each group's sample size. Something like that, right? I write in English so that the formula, right, the meaning of the formula doesn't get buried by all the algebra that we work on, right? So next is SSE. SSE is similarly sum of squares. When we talk about sum of squares, there's a strong smell of variance involved, right now, yeah? You just divide by the number of samples, then that is already variance. So that is the kind of thing that we are doing, the number of samples, because number of overall samples is n, but they're separated or they're categorized into groups, not necessarily evenly. Okay, so the number of groups is also a number of samples in within the ANOVA calculation. Because it looks at the n number of measurements not as a linear sequence, but separated into groups. In fact, when the data comes in, we already separated them into groups. And then we add up the group sizes to give n. So actually, we get n1, n2, n3 first. Then we add them up and we get n. So why 3? Because in our real life, the 3 groups have different meanings. So for example, temp staff worker, contract staff worker, permanent staff worker. So 3 groups, which makes sense, right? So we ask them, how many hours do you work? How many overtime hours do you work? Something like that. So then we gather information, and of course we'll park those numbers correspondingly in each group, right? So when the data arrives, it's already in a table form. So the sum of squares of the deviations from the overall mean means we treat all the numbers as sequential, take the average. That's the x bar. It's like discard the boundaries of the groups, treat everything as one big population, one big sample, take the average, that's my x bar. So we find the group means. So 10 workers, we find their average hours, that's the group mean, so x1 bar, x2 bar, x3 bar. Okay, x1 bar, away the difference, minus x bar, then we square it. x2 bar away from x bar, then we square it, and so on. But weighted by each group sample size. So x1 bar minus x bar, bracket square, then times n1. So weighted by the sample size. Same thing here, right? But now it's happening within group. Okay, so deviations of each data from its own group's mean. Okay, so now we have temp staff. Let's say we have 3 numbers, 6, 5, and 7, right? So 6 minus x bar, 6 minus x1 bar, because it's from its own group's mean, it belongs to group 1, right? So bracket square, that's a square, and that's all. And keep adding. Then 5 minus x1 bar, squared. And then 7 minus x1 bar, then squared. That's the SSE. So that's usually also called the within group variation or variance. So within group variations. Reason why we call it variations, to distinguish it from variance, because variance has a specific formula, right? Divided by n-1 for sample. But we didn't divide, we just sum the squares, which is mathematically easier to deal with. Just a summation, no division, like this here, right? But you don't want to call this variance. It would be very confusing, right? So that's why we call it variation. So this is called between groups. So oftentimes you will see within group and between group variations. Like this. Then we divide by the simulated sample size, right? Because here the SST deals with the group means as a number. So if your first group has 100 numbers, it's summarized into x1 bar, just one number, right? So each group has one number. That number's deviation from overall x bar, right? X bar is the average mean of all data, regardless of group boundaries. So tear down the group's temporary boundaries and average up all the numbers. So that's our calculation. That's it, right? And it is f-test statistic because essentially it is a variance divided by variance distribution. So f is a standard distribution. Standard means it's constructed mathematically, just like normal distribution. So artificial in some sense. So f requires two degrees of freedom. So unlike t distribution, only one. So the real f should be written as the numerator degrees of freedom, comma, the denominator degrees of freedom. And it's non-symmetrical, so don't mix them up. Numerator is numerator. You swap it, the f value will be, or the critical value for f will be different. So always follow df1, comma df2. The numerator, comma denominator. And you know why now, right? Because numerator, so it's very systematic. Even though it may look complex at first, it's not that difficult to understand. Okay. So that's the calculation aspect, right? But what really is involved is that we are looking at the population. Okay, so now again I moved wrong. Okay, so now it's for me to park myself on the left side. Okay, so what's the idea involving ANOVA? The idea is that we have three populations. So maybe the populations should be here. We have three populations: x1, x2, x3. And if you have more, then more, right? So I'm just going to stop at 3 here. And the idea is they are having sort of like a mu1, mu2, mu3, right? So mu1, mu2, and mu3. Now, not necessarily equally spaced. We also don't know where they are. Remember, we are trying to find out whether they are the same. So if we know that they are split apart, then end of story. If we know their number, this is 1.1, this is 1.2, this is 1.3, then end of story. Clearly, they are not equal, right? So the idea is that the parent distribution will be like this, maybe even a bit skewed, will be like this, having a center there and very right skewed, that's why it's off center, and maybe like this. Okay, that's a parent distributions, which we don't know and no time to find out, not enough resources to find out. Right? So what we do is we perform sampling. All right, and then we calculate. Now, reason why we want to look at variance, we're trying to test whether mu1 equals to mu2 equals to mu3, right? But we are looking at variance. Why? Because in this situation, we ask, could mu1, mu2, mu3 be basically the same? Are we really very, very sure in our ability to tell them apart? Right? So that's the main question to answer. And the key lies in the analysis of the individual variances. Variances as in sigma 1 square, sigma 2 square. But we can also deal with the squared differences or the relative squared differences, as we'll see in a while. So let me just talk about two cases. One case is when we have mu1, mu2, mu3, but the spread of the deviations are so large, so nebulous, right? So for example, it could be that population 1, right? That's population 1. Population 2, population 3, so that at any sample value here, for example, right? So you capture a measurement. Remember, this is our measurement, right? Our measurement is on the x-axis. So we use sensor, we use our eyes, we use judgment. We measure one point, and that point is 1.2. Then we say, is this 1.2 belonging to population 2 or population 3 or population 1? But because the tail for population 1 is so fat, right? That means there's a high chance that it is also population 1. Of course, we can now see with our eyes that it is population more likely to be population 2. But look, maybe it's at the intersection. Theoretically, it's also possible, equally possible that it's population 3. So one measurement can't tell us what which population that measurement belongs to, right? Or sometimes in other situations we say, okay, fine, now population 3's turn. Then we measure and it's 1.2, then we know that belongs to population 3. But if you measure one, the next instance you measure population 2, you also get 1.2. So now just from 1.2, can we point estimate population 2 and 3 apart and say that they are different, right? So then the next measurement, let's say we also happen to get 1.2 because it's also quite likely, right, that we get 1. So you see, that's the problem. Now, how about another situation? Also x1, x2, x3, also mu1, mu2, mu3, right? So we have mu1, mu2, mu3. But this time round, remember, we're not supposed to see the mountains, the clouds, right? Okay, so this time round, the populations are really very distinct, very well defined. Okay? It's like taking a picture with a camera. A low resolution camera will be the second situation, right? Because when we see a blur, it's like taking a camera with the maximum resolution 640 by 360. You take a picture, far away, there seems to be a little arrow. Is that a bird? Is that a plane? Is that Superman? We don't know because it's all a blur right now. You can't tell. And when you magnify it, what do you get? Pixelation, right? So all blockish, and you still can't tell. And that's this thing, because you look at that pixel, that huge block mosaic, right? You can't tell whether it's a bird, it's a plane, it's Superman. Can't tell. The shape is not very clear, right? But if we change it to a high resolution camera, 8K camera, right? So if we take a picture, and because it's very dense pixels, meaning a lot more sensors per, per square millimeters, then those extra resolution will allow us to be very clear, right? There's no ambiguity. So it will be this case when we have high resolution camera. So when we make a measurement, my measurement now is the shape, right? So just now I was saying 1.1, 1.2, 1.3. You can say 1.1 and 1.2 and 1.3, they are very close, or you can say they are very far apart. In this case, we will say they are very far apart. If you measure 1.1, it's a bird, right? If you measure 1.2, it's a plane. If you measure 1.3, it's Superman. Now, of course, we don't measure. We use our eyes to detect the shape, right? And say that the similarity value of this tail looks very feathery, so should be a bird, quite clearly. Right? Or we look at the tail, and because there are so many pixels, 10 to 50 pixels to describe the tail, and it looks metallic, a little bit shiny, then we conclude it can't be a bird. It looks like a plane, right? If it looks like, there seems to be a few toes there. I count 1, 2, 3, 4, 5 toes. I think it's Superman, right? So it's very, very clear once you have higher resolution to narrow down the variance. So I hope now you see why variance plays a big part in trying to distinguish the three means, the population means. And in my bird plane Superman example, the mean is a picture, it's a shape, it's identification of bird plane Superman, right? Um, but it also goes with measurements, with other stuff like the AI, right? So, which one does it belong to is what analysis variance is all about. So now I hope you see why we're so interested in looking at the variance rather than just looking at the means themselves. Okay, what I like to do now is to first draw a boundary. Okay, to give us a bit of room and clarity. Okay, so now what I want to do is to just quickly give an illustration that we have three sets of data. ABC, I just call it generically ABC, right? So it can be temp staff worker, contract staff worker, and permanent staff worker who are supposed to be sort of audited on their benefits or maybe happiness with the company, right? Something like that. So, so after a series of interviews, they are converted to numbers and allow me the luxury of just having simple integers to reflect a sample size of 3, right? Here, 5, 6, 9, 4, 6, sample size of 5, and it's purposely shown with different sample sizes to illustrate to you that for equality test, we for ANOVA, it is unpaired. That means you are also unable often to ensure that you have equal number of sample sizes. Okay, this is our input, right? So we gather these happiness index. Are you happy with our company? Convert all the questionnaires into numbers. We get these. Okay, then what happens? Well, next is we start our calculations. Okay, so first thing first is we calculate our x bar. Right, x bar is to treat everything as one sequential data set, tentatively ignoring the boundaries. So if you take the average, I hope you get what I get, which is 6.5833. Okay. Then you can also get the overall squares. Overall squares is the SS all. Okay, so the sum of squares of all data, right, is basically summing all the data, summing all the data from 1 to n. Yeah, n is n1 plus n2 plus n3. And number here, sample size here, right? So this is n1, this is 5, this is 4, clearly, right? Okay, so sum of all the data xi from x bar, and then squared. So this is the summing of all these 6 minus 6.5833 squared. 5 minus 6.5833 squared. I won't write them down, but you can try yourself. The number I get is 26.9167. Okay, that means this is the overall squares. That's it. You cannot get more than this. So this is the overall squares. So what I'm going to do is to try to illustrate it with the group and calculations. So the group x bar, that is x1 bar, x2 bar, and x3 bar, right, is going to give us vertical sum, vertical average. So 6, 5, 7, you get 6. 5, 6, 9, 4, 6, vertically. So vertical down, right? You will get 6 as well. Vertical down, you get 7.75 exact. Okay. Then what we can do is to calculate the between, right? So the group between, the sum of squares between the groups. Between the groups means let each group, like 6, 5, and 7, be represented by 6. Okay, so 6 minus 6.5833 squared, then times back the 3 here, the sample size. Okay, so if you do that, then you get 1.0208, right? Now I got to expand a little bit. Second one, 1.7014. Third one, 5.4444. Okay, so this is actually a bit like saying, if I were to replace A's data entirely with its own mean, like 666. First of all, the average of 666 will be 6, right? Then use each of the numbers to 6 minus this square, plus 6 minus this square, plus 6 minus, you can see it's the same, right? So that's why we multiply by the number of samples by 3. So here, the group mean is the same. So by right, we should get the same, but this group B has got larger sample size. So no wonder the final here group, right here, the sum of squares is larger than. And here the sample size is smaller, but the group mean is more, is further away, right? More distance away from the overall mean. So this number is, because of square, blown up even further. And I shouldn't be writing SST because SST is the sum of all these. So I should write the individual group squares, right? So the group based, right, sum of squares. Xi minus x bar squared times ni. So that will be I equals to 1, 2, and 3. Okay, so xi minus x bar squared times ni. So we get this. So of course we can sum them up. To get SST, that's our 8.1667. If you add up these, you will get 8.1667. Let's do the group xi minus xj bar. I can put a j here, can I not? Okay, I change it to j. J refers to the index for the group. So j equals to 1, 2, 3. So here, xi will be the individual data inside. Right? So the individual data inside minus its own mean, then squared. Okay. Then keep minus its own mean, then squared, then multiplied by the, well, you basically just keep adding them up. Add them all up. Sum over all the I from 1 to nj. Okay, that will be the correct way to say it, but looking a little bit more complex. First thing first, check that it is 2. This is easier to check, right? Because it's small. So 6 minus 6 squared plus 0. 5 minus 6, 1. 1 square is 1. 7 minus 6, that's 1. 1 square is 1. So 1 plus 1, 2. Right? So it's quite easy to verify that this is the case. Okay, then we keep doing that quickly. 2.75. And again, this is the reason why I do this. You can suspect that it is leading us to, if you sum this row up, you should get SSE. Okay, so our SSE gives us 18.75. 18.75. So in that sense, it's saying that within each group, there's a lot of noise, a lot of sum of squares deviation. So it's looking more like the first case than the second case now, right? Looking more like this diffusion, because the denominator, which is the noise or deviation or fluctuations within each group, is adding up to a lot larger than the difference from the overall mean. So the overall mean is somewhere, maybe here, right? So the overall mean is this mean minus this mean minus this, then square. This mean minus this, then square. Right. So and of course it starts to get very ugly because of all the squaring and all the differences, and there are so many points, 4 points there. Right? So but you can see from this summary that the inside noise, think of SSE as the inside fluctuations, inside noise, let's say, because this is clarity, this is noisiness, right? So the internal noise of each group is basically a lot more than the between groups. But we haven't standardized it to the per unit measurement yet, remember? Yeah, so we have to do that. Okay, so at this point, we can calculate the what we call the standardized version. So the standardized version is the mean sum of squares for between groups. Typically, books will call it MST. This I didn't really introduce early on, but it is just the numerator of the test statistic. So it's just like breaking it down to one more step. That's all. So SST divided by K minus 1. And of course, we can note that the degree of freedom for SST is K minus 1 is equal to 2. The degree of freedom for SSE is N minus K. It is equal to, what is our N? 3, 5, 4. So 9, 12. 12 minus 3, that's 9. Yeah, so our F test statistic will be measured against the critical value, right, with degrees of freedom 2 and 2, 9. So MST, we get SST over K over degree of freedom 1, basically, right? So we get 4.0833, and MSE, you will get SSE over N minus K, right? So N minus K is a much larger number, so we might be surprised. Let's see. After the division, we get 2.0833. So now it's not so obvious, right? Now, so after standardizing to per measurement average sum of squares, so this will be the average sum of squares. On a per measurement basis, what is the sort of relative strength of the between group, between all groups, and the within group? Look at all the internal noises. So what is this? So after the division, you should get F equals to 1.96. Now, just like our 1 population and 2 population means test, right? We always need a distribution. So we covered this in the general hypothesis test video, that the distribution is very closely related to the test statistic. So we have chosen the F distribution. We need to use the F test statistic, so we have to use the F distribution. So let's try to sketch what F distribution could look like. Okay, So first thing first is the F distribution. It changes shape depending on the degree of freedom, but especially when degree of freedom is very few, like 2 and 2, 2 and 3, 1 and 2, that kind of thing, then the shape totally becomes unrecognizable from general F distribution with other larger numbers of degrees of freedom. So let's look at the more healthy form, the more general form. It starts from 0, goes upwards very sharply, then it kind of tapers off until infinity. A little bit looking like chi-square also. So, but you just do a sketch like that will do. And as usual, we want to have a sort of a significance area. Let's just call it 5%. Right, so alpha equals to 5%. Okay. And we need to calculate the inverse CDF for F distribution for 95%, right? So we get this number. This time around, we can't use the Z or the T trick. We just do a 5% left side, then drop the minus sign, but F is entirely positive, so there's no minus sign. So we just have to now do the adjustment way, not the dropping of minus sign way. So we take the inverse CDF of 1 minus alpha. 1 minus alpha will give us 95%. So we take, like in Excel, you can have F dot INV, inverse of F distribution. In R, you can do QF. QF, that means Q is to get back the quantile for 95%. And no matter what you do, you finally should get a FC, let's call it, right? The FC of 4.2565. So that's our critical value. Now, notice something, that in this case, our rejection region is on the right side. So if you recall, our 1 and 2 population mean test depends on the H1, right? So that's our H1. Okay, at least one of this. Now we no longer have a clue here. So you have to kind of remember that for F distribution, it's always right-sided, unless when you're doing confidence interval for variance, which is another topic altogether. But for hypothesis tests, ANOVA, and you will encounter F again in regression, right? So linear regression, we always use the right side to reject, because the ratio, you see that F-test statistic is constructed from MST over MSE to get this. So I think I better put in this bracket formula. MST over MSE, right? So it's a ratio of the squared differences. In other words, it's like ratio of 2 squares. They are derived, but they also derived from measurements. So the ratio of 2 squares almost always suggests the link to F distribution. Maybe another way to think about it, F distribution is a mathematical construction designed to describe the distribution of ratio of squares. So you have these. Now let's look at 1.96. Where is 1.96? Oh, it is like here, right? Inside, right? So if 4 is here, infinity is to the right, then the Google pin should be dropped right here. Meaning our p-value should be larger than 5%, right? So what is our p-value? Using the CDF function for F, like in Excel, it will be F dot dist, right? In R, it will be PF, right? So you can calculate p-value to get, and you don't have to times 2 because it is one tail. So kind of everything is a bit strange, right? Our hypothesis is equality, equal a lot, right? But it is actually a right tail test, not left tail, not two tail. So our p-value is right tail you don't have to times 2. So after the f dot dist, you should get 0.1965. Not surprising, right? A lot larger than 5%. Not surprising because certainly the Google pin is far to the left of alpha or FC for that matter. So over here, this points to exactly f equals to 1.96. Can see here? Yes, okay, right? So what do we do? Well, of course, we practice what we have learned about hypothesis test conclusion, and we say since p value, this part will be boring if you have been looking at earlier videos because it is supposed to be boring. There's no creativity here, right? We would just say the obvious fact. Since p value is 1965 is not lesser than alpha, which is 5%, for that matter, even 10%, we fail to reject, right? So we do not reject H naught and say what H naught says in English, not in Greek, not in mu, not in something strange, right? So we say that we actually want to say mu1, mu2, mu3, they are the same, right? So we want to say that the populate and conclude that the conclusion is always about population mean. Never make the same mistakes as some students during exams. Conclude that the sample mean, all right? Conclude that x bar is never about x bar. Also, conclude that population mean, let's say happiness for temp staff, contract staff, and permanent staff, right? For A, B, and C, population means are the same, are equal, but you got to qualify the significance level at 5% significance level. Right, don't say alpha is 5%, because again, you're introducing Greek letter. And why we have to say significance level is that this alpha, right, is going to decide whether you reject or not reject. So especially when p-value is near to alpha, right? We talked about that before. So the conclusion always has to have a 5%. Now, sometimes in journals and literature, you might see people skipping the entire thing, right? Because they have more things to say. They are talking about the discovery of a new drug for COVID-19. They're talking about the exciting conclusion of or findings about this effective drug of cancer for Alzheimer's disease or whatnot, right? So they have a lot more exciting things to say. And following this kind of rigidity and elaboration is really not so important in their journal or article or publications. So what they do is they say, instead of saying the whole thing, they just put bracket p-value, or rather p equals to 0.1965. And when p is so large outside the alpha-ish region, right, the 1% to 10% is the alpha region, right? But it's so much larger than the largest alpha that normal people will choose, then it's clear cut that it's not effective or it's not true, right? Especially for those journal publications that try to refute earlier claims of effectiveness or whatnot. They say drinking more tea helps to prolong your health, for example, right? So some researchers publish that, and you are the next researcher trying to disprove that. Then they say, oh, like that. Actually, all our participants, they experience the same longevity, right? So drinking tea, one group is drinking tea, the other group is not, and the other group is drinking whatever else, right? Some vitamins and all. So so we have to be aware, right, of this practice, and that practice comes not from some definition, but the editor, the publishers, the author, the research community, the the article readers all agree that, yeah, I don't have to read all these stuff, right? Just give me the p-value, and if you write p-value is 0.00001, I already know it's very significant. No wonder you are so excited, right? So if you Google around and you don't have to read through the entire article, but scan for those bracket p equals to, especially when they say, is we found that drinking more tea is helpful to extend longevity. Bracket p equals to 0.00005. And then that's it, right? That is providing the evidence that our finding is significant no matter what alpha you choose. Correct or not? Yeah. So that's the way to be able to consume more, because once you get used to it, you know that at the back of the author's mind, they meant this. You are also able to read what they publish, so you can gain more knowledge, right? When otherwise, if you didn't learn this stuff in statistics, if you didn't learn this communication language between advanced discoverers and learners and scientists in the human community, trying to tell us, the second layer, third tier, fourth tier layer people, these exciting discovery of nature, then you cannot absorb those information. Or you are unable to understand. It's just like looking at a third language, fourth language, a language that you haven't learned, right? Maybe it's Portuguese, maybe it's French. You haven't learned, and you look at that literature, you don't understand, you lose interest. But maybe there's wisdom in that, right? So I hope by now you are able to have a better grasp, right, of ANOVA, and be able to take the initiative to apply them whenever such situations occur in practice in your life and your career. Thank you very much for your attention. I'll see you in the next video. Bye.